The purpose of the Waves on a String lab is to observe relationships between frequency, wavelength, and the speed of a wave on a string. We can see how these relationships change with tension and by varying the frequency and seeing what happens to the wavelength and speed. You will also study the properties of resonance and the formation of standing waves on a string. Let's go through a little refresher on waves first. The wavelength is defined as the distance that the wave repeats itself. We can also define the amplitude as the height of the crest or the depth of the trough of a wave from that x-axis. The period is similar to the wavelength in that it is the time it takes the wave to repeat itself. What we're mostly going to be interested in is the frequency. The frequency is the number of times the wave repeats itself in a second. The equation for frequency is 1 over period, and the units for frequency are 1 over second. Now the speed of a traveling wave can be found as distance over time. Since the wavelength is the distance the wave repeats itself, and the period is the time the wave repeats itself, these offer us a great opportunity to calculate the speed of a wave. And again, since frequency is 1 over the period, this equation reduces to just wavelength and frequency. So again, here's your wave. You can measure the wavelength as a distance it repeats itself. You can measure the time that wave repeats itself, and you know the speed of the traveling wave. Now a standing wave is a pattern that is produced by two waves traveling in opposite directions. And so in this particular picture, you have a string that's fixed at both ends, and the wave is traveling in one direction. It hits the end, and it reflects back upon itself. This reflection actually allows the wave to amplify and creates the standing wave pattern. So a few definitions. A node is considered a place where the displacement of the string from the x-axis is a 0. So a node is a 0 place, and an antinode is a maximum. So you notice up here we have antinodes in the middle of the large distance here, and a node is at the small distance here. In activity 1, we're going to be calculating the speed of a traveling wave on the string. In general, the speed on a string is constant and depends on the material the string is made of. That's the linear mass density and the tension that the string is under. So making the string tighter and lighter increases the pulse speed, and making the string looser and heavier slows the pulse speed. In activity 1, we're going to investigate the speed of a wave with different tensions applied. The way we're going to do this is directly measuring the distance and time to find speed for a particular tension. We're going to use a simulation for this. First thing you want to do is open your PhET Waves on a String simulation, and there are some values you need to set first. We want to look at a pulse. We want this to have a fixed end. That's the C-clamp. We want to make sure there's no damping, and the tension is set low to begin, but you're going to change this throughout this activity. In order to measure the distance, you need to turn on your ruler, and in order to measure the time, you need to turn on the timer. The amplitude is by default set to 0.75 centimeters, and the pulse width is set to half a second. We're going to leave those as is for now. So calculating the speed of the traveling wave on the string, you're going to use the ruler. You want to set the 0 mark right underneath the green dot. And you're going to measure the time using the timer for 1 pulse to make 5 round trips. In activity 2, we're going to use 2 different ways to find the speed of the wave on a string experimentally. Similar to activity 1, we're going to directly measure the distance in time. However, we're also going to measure the frequency and the wavelength and calculate the speed using the frequency times the wavelength equation. For this particular activity, we're using the same simulation, but we're going to set some different variables. We're going to set our simulation to oscillate. we want it to have no end, so there's a little window at the end of it. You want to keep your damping on none and your amplitude at 0.75 centimeters. And again, you're going to use your ruler and your timer. It might be easier to measure the wavelength if you get to use the slow motion tool and also the start and pause button on the simulation. We're going to fill out this table. You'll notice that we have 3 different tension levels and also 3 different frequencies. So you'll set the tension and the frequency. And after setting the tension and the frequency, you'll measure the wavelength using the ruler and calculate the speed from frequency and wavelength. You'll also measure the distance traveled on the string and the time traveled using the timer and measure the speed using distance over time. Now keep in mind the distance traveled is going to be the same because the string is not changing length at all. So this value is actually going to be the same for all of your different trials. However, your frequency and your tension are going to change, so therefore your wavelength and your speed and your time traveled are going to change. In the third activity, we're going to generate standing waves of different harmonics. So recall that harmonic is really the designator of how many antinodes you have in a particular standing wave. So this particular standing wave has 2 antinodes, so we call it a second harmonic. So the measurement of the string can be used to determine the wavelength by recognizing that n half wavelengths must fit between the length of a fixed string. So in other words, this is a second harmonic. It's got 2 antinodes. I can find the wavelength of that second harmonic by measuring the length from one end to the other. And I'm going to take the value of 2 divided by the number of antinodes. So 2 divided by 2 is 1. The wavelength for this particular harmonic is just 1 times the length of the string. So remember, 1 wavelength is equal to 2 antinodes, or another way you could think of it is the distance between 2 nodes is half a wavelength. So this distance is always half a wavelength. So the variables we're going to set this time, we're going to keep it on oscillate. However, we do want to change the amplitude to 0.2 centimeters because otherwise the amplitude of this standing wave gets very large. We're going to change this to a fixed end. And we want to keep the tension on medium. We're not going to change the tension in this activity. We want to keep it on medium all the time. Make sure you set that correctly or the values that you get will not match those that we're expecting. So again, you're going to determine the wavelength by looking at the number of antinodes that you should have for your wave. So you should have 2 antinodes, so 2 divided by 2 is 1. So 1 times the length should be your wavelength. You're going to calculate the frequency based on the known speed of the wave at medium tension. Remember, you set your wave to medium tension. So you look up what the speed should be at medium tension. You've calculated your wavelength, and you can use that to find your frequency. So frequency equals speed divided by wavelength. After you calculate your frequency, you're going to dial it in. Right here, you're going to change that frequency, you're going to put in the known value, and you're going to see if you have a standing wave. If you don't have a standing wave that you're expecting, you might check your calculations. You're also going to take a screenshot of that wave so you can prove that you got the correct harmonic. As always, if you've got any questions about this lab, if you're struggling with getting the simulation to run, or if you're unclear about the instructions, the preferred method is to ask that question through their question forum, or you can email your instructor directly using the instructor contact information posted on the top of the Agilent page. Thank you, and I hope you enjoy this lab.